Okay, now here we will be discussing about uh, LeetCode's weekly contest 502. So the first question of it is check adjacent digit differences. You are given a string S consisting of digits and return true if the absolute difference between every pair of adjacent digits is at most 2, otherwise return false. The absolute difference between A and B is defined as absolute A minus B. So what we need to do basically is uh, just know whether or not uh, every adjacent digits have a difference of at most 2 or not. So it can be done with a simple loop. So first we need to store the length of the string, and then we go to a simple loop and check. Uh, let's say store the numbers into variables. First num is equals to s of I minus 1, and second num is equals to s of I. Now these needs to be integers, so let's subtract 0 from them and then check if absolute of first num minus second num is greater than 2. We are going to simply return false. Otherwise, if it's true for every case, uh, we will be returning true. Return true. So this seems to be working fine. And there we go. So next question is count kth root in a range. So we are given three integers L, R, and K. An integer y is said to be perfect kth power if there exists an integer x such that x raised to the power k, y is equals to x raised to the power k. We have to return the number of integers in the range L and R inclusive that are perfect kth powers. Good. So basically what we need to do is find all the numbers whose kth power lies in L and R. And looking at the constants, LR can be up to 1 in R. But if you observe it, that uh, what's the highest, like if we have a number like 1 in 5 and we square it, the square of that number will be greater than R or greater than 1 in 9, that's 1 raised to the power 10, 10 raised to the power 10. So what we could do is actually brute force this, like there will be a special case if k is equals to 1, that means no need of power or anything, so we just return r minus l plus 1. These that's how many number there will be. And if uh, power is greater than 1, that means we need to check square or above, like cube or quadrant. So to do that, what we could do is just find the squares or the kth power of every number from 0 to 105 and check whether that value lies within L and R. And this can be done because K can go only up to 30 and our numbers can go up to 105 because even with the lowest number square, any further values will exceed our maximum limit. So what we need to do is for int I is equals to 0, I less than, need to go up till 25, that's the maximum, I plus plus, and here it's will be good if you use long long, so you can compare them like this. So long long, let's say well, that will be I, comma 1, then for int j is equals to element k g plus plus. To calculate the power, val times I. Now this can go like exceed the long limit. So what we can do is if val is greater than 1 in time, we could just break and set val is equals to -1, and let's maintain a count. Count is equals to, like, these are how many answers we have, so it's going to be equals to or plus equals to if L is less than equals to val and then R is greater than equals to val, and we will just simply return count. Next up is largest local value in a matrix 2. So we are given an integer n cross m integer matrix containing non-negative integers. A non-zero cell row call checks the cell near it as follows. Let X matrix row column consider every cell within X rows and X columns of a row. Ignore cells that are outside the matrix. Ignore cells that are both row distance means column and column distance are exactly X. The cell's row call is local minimum if it's non-zero and non-considered cell has value greater than X. Return an integer denoting number of local maximums. So what we basically need to do here, we will be given a matrix that will be something like this. And let's say there's a number. Should I take 2? Let's say 2. Okay. So now there will be a sub matrix around it, and it will cover the whole matrix for this case. That is 2 column from left, uh, this, and 2 column from right, 2 column up and 2 column down. So this whole matrix will be considered to check whether this value is our local maximum or not. And there's also one condition that uh, cells which have the cells where both row distance and column distance are exactly X. That is, these values will have row and column value equals to X. So these values will be ignored. So all the cells, these cells, will be considered for local maxima apart from these cells. Now how would we calculate, like, this is not getting the result, this is not getting the result, this is not, and this is not. And we need to find, there will be some values here. We need to find if this is the maximum value among all these values. And so solution would be to go to every place where there's a positive integer and check for each of its possible submatrix. But that would be too slow of a solution, like for traversing a matrix with n times m, and traversing the matrix, the valid submatrix of each value would again be n cross m time complexity. solution. So that would definitely fail. So we can't do that. So approach could be, what if we know uh, the maximum of this column, maximum of this column, maximum of this column, maximum of this column, maximum of this column. If we know maximum of this column, these column, we can take out the maximum of all of these and check whether this maximum is actually equals to our this value. Well, if it is, then it's a local maximum. We can increment our answer. But if it's not, then we can just move on to next values. Now, how will I do that? How am I sure that this will work? Because traversing the matrix to find the possible local maxima will be m%, and let's say we compute this, finding local maximum, finding maxima for a column in a bounded area. That's going to be a O of n operation. That will be a big operation times moving through all the cells. That's going to be of big of n solution. So it's a n cross m square solution, which will work for the cascade bounds are low because like 200 only. So what we could do, what we have this in, how would we solve this in big of one time? So in order to do this, what we could do is like we can go to a cubic solution. So what we can do is fix a top, fix a bottom. That is, these are the rows, and then uh, for each column, do this, fix a top and column, and keep on finding the local minimum, maximum. Like if this is the column we have to refer. And let's say the values are 1, 3, 2, 4, 5, and 2. Our top would be here, and bottom can also start from here, B. So the local maximum would be here is 1. Then the bottom moves here. Now we check. So the local maximum will be 3. Now it will move to this. Local maximum will be 3, and so on and so forth. Now the top moves down. So top moves a step down. So these all values will be filled in our pre-compute top, and it will be filled like for each bottom and whatever the column we are currently processing. Now similarly we will move bottom top down, and we will start checking from here. This 2-pointer is an n square approach, but we are calculating the maxima with this iteration only. So it will be a big of one operation to calculate maxima, and we are going through each column. So it will be a big of n square times big of 1 times m. So the overall complexity would be n square times m for pre-computation plus n times m square. So in order to do this, let's first have the number of columns in matrix of size and number of, let's do this like this, rows and matrix dot 0 dot size. These are the columns. Now let's create a pre-compute array that's going to store this for top, this for bottom, and this here for the columns. You can just specify with any value. As zeros are also there, we should like initialize them with -1, but I don't think so. Zeros would also affect them. Now let's traverse them. So for each column, let's say column starts from 0, column is less than 10, col plus plus. We need to create another variable to maintain the local maximum. Let's initialize it with -1. We cannot write this pre-compute statement outside because we have to get the pre-computation for each bottoms corresponding to this top. So we need to like store them every time we calculate a maximum. After creating this pre-computation table, what we need to do is let's just traverse the whole matrix and now the value is, so val is matrix ij if val is less than 0 or if val is less than equals to 0, you're going to get it in because you only are interested in greater than 0 values. Now once we find that this value is greater than 0, what we need to find is our left endpoint. That's going to be like this portion. Like it's possible that a matrix could be of form this, and our 2 is present here. Now these cells are not valid, but these cells are valid because uh, actual row comma column equals to x are here. That column that's not actually present. These are not valid, but it's not part of our matrix to begin with, so we don't need to consider them. What we could do is left column is equals to maximize it with 0 comma. What will be our left column? Another value that's j minus val, or I think I should take it as x because that's what's given in the question. Right column will be equals to minimum of j plus x, and now I need to do like if we are here we need to only check these columns. I don't need this one, and I don't need this one. So if left column is equals to j minus x, what we need to perform is let's also store the actual maximum value that's going to be here. That's max equal to max of maxi comma whatever the computation of this gives. So it will be I minus. So we can't just directly do this because it could also overflow. So what we need to do is what's our upper or top. Our top is I minus, not I minus, max of 0 comma I minus x. And what's our bottom is minimum of n minus 1 I plus x. But remember we need to subtract these values. So what we are going to do is add one here and subtract one here to capture the in between left sides. And now let's get the value of this. So we're going to do this and left column. Now similarly need to do for right column. Right, but here, okay, here it's also correct. Just need to change this to this, j plus x. Next up is these values that are fully taken up. So these can be calculated with for a, let's take it as k. Yes, let's take it as k. We are going to start with left column. We like this. So if left column is already calculated with, so if this is already calculated, we need to start with here. If it's not, we need to start with here. Like the right column is actually to this, so we need to loop till this. So what we are going to do is max of 0 comma a minus x plus 1 j minus x plus 1 and k is less than minimum of n minus 1 j plus x minus 1 j that is k plus plus. And what we could do is add this stuff from here, and I don't need this, so I can remove them. Right column can be changed to kth column and get this. Now if max is equals to our x, we are going to increment our answer and return our answer. Let's create a variable to store our results. What I've done here is check whether just the next value is 0 or not, like is available or not. If it is not, like we can just clip it to, like this is also a possible case where there is something values like here and 2 is present here. It's j minus x is actually live here in this column. So what we need to do is clip it here. Similarly on the right hand side. Okay, max cannot be got. Okay, so not x. Did I call something that it's not x, it's value. We need to get the value from it. So store the maximum value. Right. Oh, okay. So why is it giving me 0? even though every values okay, so the bug is in here. We don't actually need to just we actually need to also cover this j plus x minus 1 also, because we are covering this part also that actually give the ending column. Yes. Moving on to the next question. Smallest unique subarray. So it's a bit of a hard problem. So you are also given an integer. You are given an integer array. Find the minimum length of subarray that is not identical to any other subarray in nums. Return an integer denoting the minimum possible length of a such subarray. Two subarrays are considered identical if they have same length and the same elements of in corresponding positions. So what the gist of the solution, gist of the problem is that we are given a array having bunch of elements like uh, and we need to find subarrays that's unique and have smallest or shortest length. So we have these two conditions need to be required. But the solution is so let's before moving to the solution, let's uh, do this case because it actually clarifies many things. So if it's 333, if you take just this subarray, we have actually a similar subarray here and here. So subarray 3 has actually 3 count. There are 3 times. So if we take this subarray like 3 3, it also have this subarray which is 3 3. So subarray 3 3 is count 2. These two subarrays are not equal. This and this, because this index value is different. Even though they share a same index, there's one index that's different. So these two subarrays are considered different subarrays. But the subarray 3 3 3, this is actually unique. So you might be thinking, why not always select the whole subarray? Well, if you select the whole subarray, it would indeed be unique. But there's also a second condition. We have to find the shortest length one. Now, what you can think from this is binary search, because let's say you have a bunch of lengths that are possible that can go up from 1 to n, to 1 to dot 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 n. So if there's a possible k length, for this it's unique, then for every other possible value, the subarray will be unique also. We need to find the smaller one. It could be a possible answer, we need to try to find a better one. This is the easy part. Now what we need to do is try to find the unique subarray. A solution could be using map, comma, vector of int, comma, int, and we will do frequency, or rather than vector, we should do q or tag. What we could do is with binary search, we will get a mid value, and with each mid value, we are going to create uh, every possible subarray of size mid. If it's like A, B, C, D, E, F, these are not meant to be different. These are just values. It could be like A could be B, C, and C, but it just for showcasing. Like these values are there. So let's say mid is 3. What we could do create this subarray. Now insert it in map. Now map supports hashing these containers implicitly, so it can handle them. So ABC will be inserted in the frequency and its count will be set to 1. Now you can just remove this A and insert push back this B at the end. So you have B, C, D as your new container, or I should say subarray to check upon. So creating this subarrays is actually a bigger of an operation only. Like this binary search will be bigger of n log n. This creating of subarray is bigger of n here, but when we try to insert in this frequency array, it's not actually just log of n, because these containers need to be hashed, and it also takes a bigger of n time. So hashing of this DAC also take bigger of n time. So overall, it will become bigger of n times n log n. Like inserting it in the loop itself. It's going to be n log n. So the overall solution will go n log times n. Wait, it's not n log, it's log n times n times n log of n. So it will all obviously be slow. We can't do this. So what we could do, instead of storing it in this map, whose hashing function does its thing in big of, we could use our own hashing function. Like if you heard of string matching using Rabin card, we are going to do something similar. Let's say we have A, B, C, D, F, and mid is 3. What we are going to do is find the hash of these 3 values, then these 3 values, then these 3, these 3. And after that, each hash will be different. Each hash can be stored in an unordered map of, um, let's take it as long. and frequency. After that, we just need to check if there's any frequency, any subarray frequency equals to 1. Now, how can we calculate this hash? So, how Boolean hash works is we need two values, prime and not prime mode, but actually a base. So, let's take that base and a value to modulo. So, and it should be a large prime number that let's take it as 1 9 plus 7. That's in the set value for integer values, and our instants are just 25 and length is also 25. And the base is equals to the range of the values. So our range is from 1 to 25. So the number of values are 25 values. So we are just going to take that 1 So how this hashing works is, let's say if we have A, B, C, so when we do its hashing, it's going to be C plus, it's going to be B times capital B and plus A times B square. This whole value is going to be modulo. This gives a hash number that that actually identifies this string uniquely. So let's say if you have ACB, then C will be B will be here, and C will get multiplied by B, and we will still have B square. But this maintains the uniqueness of values. Now, what if a D comes in? For this, let's say it's A, B, C, D, or A, B, C, D. No, it's going to be this. Now, let's say a D comes up. So, what will be its value? It's going to be B times B square plus C times B plus D times modulo. So, what you notice is this part and this part is same, just a difference of B. So what we could do is let's take this value as x and this value as 1. What we could do is x make it a times b square. We could remove this value. Just forget about the modulo format. The modulo is not actually in the operations. And then what we are going to do is multiply this thing with b, the base, that actually converts it to this value. And in the end, we are going to add it with d. So this results in b times b plus c. This results in b times b square plus cb. And this will just add it b times b square plus cb plus d. And that's the result we need. And we do modulos in needed places. So that's how we are going to do hashing. So this hashing is done in big of 1. That means what and operation insertion deletion of another method also big of 1. And basically our whole check becomes big of n plus big of let's say n for traversing all the subarrays, all the possible subarrays of length traversing all subarray of length equals to mid, whatever that value is. Yes, so the overall time complexity will be log of n times big of n plus n, that equals to log of times n. And log n solution will be this. Let's put it up. Our value is our length is dumps dot size. Left could go all up to 1 and right can go up to whatever the maximum, like the whole subarray, the whole array can be taken as the subarray for the uniqueness. Now the mid value is equals to r minus n divided by 2. We will be having a function that's going to take nums and mid, and if any other parameter need to be passed, we can edit this function. Now if this check is true, that means there's a subarray of length mid that is unique. That means we need to find a smaller one, so we can just go mid. Otherwise we have to go further, like increase the size. So we can just return L. Next part is creating a function f. So let's do this. That's going to return a bool const vector of int nums const int. Let's get it there. Now we also need the base value, that's going to be 25, and the modulo value, that's going to be 29 plus 7, and these not need to be, but these can overflow because nums of I is 25, and let's say we multiply with a base b of 25, it could just overflow. So let's also get the size here, and let's have a hash value that's going to be equals to 0 for now, and a place to store our all hash values. So hashes, and we need to go to mid and calculate the hash. So hash is going to be hash equals to hash first of all move this whole thing b. Now hash is equals to hash plus nums of I modulo n. So this does calculate our hash for the first subarray of length mid. We also need something like the maximum power. So let's take the max power. What it is just the maximum power a hash function have, like the maximum power of base hash function have, the multiple of it. So times what we are going to do is patch it with b modulo n. So m power is basically just m power, basically with this value. So this is going to be something like b of k. We are not going to complete it again and again. We're just going to complete it once and store in maximum power. Why would you say? Because we need to subtract this. So we need to subtract first of all compute this a times maximum power of it. it can be calculated with this and power. Now what we need to do is maintain a two pointer, the left pointer and the right pointer. That's going to get 10 while j is less than 10. What we are going to do is, first of all, subtract what's already present. Before that, what we need to do is actually store the hash of this first subarray. That's hashes of hash plus plus. Now subtract the first element. That's going to be hash is equal to hash minus whatever the first value is times our m power. Need to modulate with m, and this value needs to be added with m, and we add m here because in modulo operation, after doing a subtraction, uh, the whole value would go in negative, so we basically add up at the modulo itself, so it remains positive. So here the subtraction is done. Now what we need to do is multiplication with base. Then what we need to do is addition of the right value. So this is our new hash. Now need to store this in hashes and then move each pointers to the right. Now another operation is for auto. Let's look through our hashes and check if any hash is count is equal to 1. If it is, then we return true. If it is not, we return false. I'm skeptical about this binary search, but I think we should go for it. So what's len? Also, len is actually len. Then minus 1 I plus plus. Okay, it's looking good to me. Nice. Okay, so sign integer overflow. Okay, so what's happening is our hash is in, that is fine. Our empower is in, that is fine because it's getting moduloed out. But the operations here are not good because these needed to be converted into long. This multiplication could overflow. And let's convert this into long also. This multiplication could also overflow. So for every hash times b, I need to do long. So it does not overflow. This won't overflow because hash and nums of I will be just like within the integral range, so it's okay. Okay, so this can also overflow. Need to convert this. Well, it would be better if I just used long for every data type in the get-go, but yeah, you can use that. It's fine. So let's use this test case to check if we are getting the runtime errors. Okay, it's passing now. And there you go. That's all for now. All 4 questions solved for the LeetCode question contest.